This is the algebra lecture 23 and chapter 4. Let me start with it. So let me start with today's lecture. Here I have to find kernel of adjoint homomorphism. Now let me start with it. I have to know the definition or the statement, I can say, of the adjoint homomorphism. So for that, first say let L be a Lie algebra. Then let add of L tending to GL of L be an adjoint homomorphism. Let this be the adjoint homomorphism such that add of x is equal to add of x for all x belongs to L, and add of x L tending to L such that add of x into y is equal to leave bracket of x comma y for all x comma y belongs to L. This you all have to write, okay, from the definition of adjoint homomorphism. Then what you'll have to do is you'll have to show that kernel of this add of x, okay, I have to prove that. So for that, what I will do is kernel of add, let me do it on the next page. To prove that kernel of add of x, let kernel of add is equal to x belongs to L, where add of x is equal to 0. Okay. Now this statement comes from where? You all have to know what is the kernel of that one note I have given you all. Wait, let me go to that note. Yeah, see this note. Kernel of phi is an ideal of L, so that whatever it is, but kernel of phi is what? It is equal to nothing but x belongs to L, where phi of x is equal to 0. But what is there? Kernel of phi. There what is there? Kernel of add is there. So add of that x is equal to 0, I said, for x belongs to L. Okay. So that thing I have applied over here. So that this is equal to 0. That is from what is the kernel statement, or I have given you all the note. Then this is equal to what? X belongs to L, where add of x into y is equal to 0. Add of x of y is equal to 0 for all y belongs to L. Can you write for all like this way? This symbol you will use, okay, for all. Anyways, now why this is equal to 0? I have told you why I said this is equal to 0, okay, from that kernel definition. But the thing is that why I am saying that this is equal to 0, because this add is what? It is nothing but a adjoint homomorphism. If your adjoint homomorphism is equal to 0, then it becomes 0 homomorphism, right? So that's why you take anything, it will become 0. Any value you plug it, it will give you all only 0, because it becomes 0 homomorphism, okay? So x belongs to L, add of x of y is equal to 0 for all y belongs to L, okay? That's why it is 0. Now, why I have told you all. Now this is equal to what? X belongs to L, where what is this add of x of y? Is nothing but from the definition all see. What is add of x of y? Leave bracket of x comma y. Plug it over here, and this is equal to 0 for all y belongs to L. Now from where I have taken this? From the definition of, this is the definition of center of Lie algebra. So write it z of L. Now this is equal to z of L. So finally we found out the kernel of adjoint homomorphism, okay? So next I will be doing is, I'll turn the page. Next I will be doing is let L1 and L2 be the two Lie algebras, and let phi from L1 to L2 be an homomorphism such that kernel of phi, and this is what I am, is what? Image of phi is an ideal of L1 and is a Lie subalgebra of L2. So basically what I need to do is I have to show that kernel of phi is an ideal of L1 and image of phi is a Lie subalgebra of L2 I have to prove, okay? Now let me start with the proof. So first what I have done is let x belongs to kernel of phi, where y belongs to L1. Okay, so now tell me, what is kernel of phi? See, kernel of phi is nothing but x belongs to L, where phi of x is equal to 0. But for what it was, kernel of phi is an idol of L, right? So that's why I've said, if it is L1, suppose, if it belongs to L, okay? So what would have come here? L1, right? Now let me do this. And one more thing you'll have to know the definition of, now to know this properly, like you'll have to know what is a Lie algebra, what is a homomorphism, and what is an idol, okay? So now let us move to, let us see like what is an homomorphism. This is the solution that x belongs to kernel of phi, y belongs to L1, I say. Now this kernel, I have told you all, kernel of phi is what? Where phi of x is equal to, x belongs to L, where my phi of x is equal to 0, right? It will x1, x belongs to L1 it was, because I have to show that kernel of phi belongs to, is an idol of L1 I have to show, right? Now this implies what? Phi of x comma y. I can just put those brackets, okay? So this is from what? The homomorphism definition, okay? Phi of x comma y is equal to phi of x comma phi of y is equal to 0. Now why this is equal to 0? Because of what is kernel of phi? Where x belongs to L1, where my phi of x, see wait, let me first, that step I have got it from homomorphism. From here, if L1 and L2 are the Lie algebras over a field F, then we say that a map phi from L1 to L2 is a homomorphism if phi is a linear map and phi of x comma y is equal to phi of x comma phi of y for all x comma y belongs to L1. So I have brought this here, this side, okay? From this, and this is equal to 0 because of this. What is kernel of phi? Where my phi of x is equal to 0. Hence phi of x is equal to 0. Now this implies what? I have to show that my kernel of phi is an idol of L1. For that, what I need to do is, I have to show that my Lie bracket of x comma y belongs to kernel of phi because of this definition. Idol. Now what is an idol? Let L be a Lie algebra and I be the subalgebra of L. Then this I is said to be an idol of this L if the Lie bracket of x comma y, Lie bracket of x comma y belongs to this I. For all x belongs to L and y belongs to I. So what should happen? This Lie bracket should belong to kernel of phi, right? So that's what I have done it over here. So this implies Lie bracket of x comma y belongs to kernel of phi. So which implies nothing but if this belongs to phi, that means kernel of phi is an idol of L1. Okay, now what I'm supposed to show? Now kernel of phi is an idol of L1 I have showed. Now I have to show that the image of phi is an Lie subalgebra or Lie subalgebra of L2 I have to show, right? Let me start with that. So let x comma y belongs to image of phi. This is nothing but image of phi, okay? Now this implies x is equal to phi of x1 comma y belongs to phi of y1 for some x1 comma y1 belonging to L1. Now this will imply nothing but Lie brackets of x comma y is equal to, now what is my x? Phi of x1, write it here. Then comma, what is my y? Phi of y1. Now this is what? Nothing but from the homomorphism, what it is? Phi of x1 comma Lie bracket of x1 comma y1. Now this implies nothing but Lie bracket of x comma y belongs to image of phi, which implies nothing but image of phi is a Lie subalgebra of L2. Now next I will be doing is about the algebra. Okay, so I will be doing what is algebras, and algebra over a field F is a vector space A over a field F. Okay, it's a vector space A over a field F. together with bilinear map A cross A tending to A and x comma y tending to x into y. We say that x, y is the product of x and y. Okay. So now one more point you all take down. The algebra A is said to be associative if x comma y into z is equal to x into, what is this? Y of z, right? Wait, this is not, comma is not there over here, okay? It is this slight mistake I have done. You can just change it. It is, let me cancel this. It is nothing but xy of z is equal to x of yz, okay? Put the bracket for all x comma y comma z belonging to A. That comma thing is not there, okay? That comma thing is not there. This comma is not there. Just x into y of z is equal to x of y of z, okay? It is like this. So just do the correction over here. Now next is what? Next let me do. Next is one exercise 1.7. Let L be a Lie algebra. Show that the Lie bracket is associative. That is, Lie bracket of x comma y comma z is equal to Lie bracket of x comma this inside y into comma z for all x comma y comma z belonging to L if and only if for all a comma b belongs to L, the commutator of a comma b, commutator of this is a commutator, or you can even say it is a Lie bracket, okay, lies in Z of L. What is Z of L? Center of Lie algebra, right? Okay, let me start with the proof. So solution, take this x comma y comma z, this is equal to, take this one first, write this here, for all x comma y comma z belonging to L, okay. Now this implies what? X comma y comma z plus z comma x comma y is equal to 0 for all x comma y comma z belongs to L. Now what I'll do is, this implies like z comma y comma z comma x, this bracket, put the Lie brackets, okay, is equal to 0. Now this is for all x comma y comma z belonging to L. This I have taken from the Jacobi's identity, okay. Now finally you all can say this implies z comma x belongs to Z of L for all x comma z belongs to L. And how you all will prove the converse of this? If a comma b belongs to Z of L for all a comma b belongs to L, write down this a comma this b comma c, Lie bracket is equal to 0 is equal to a comma b comma c for all a b c belongs to L. This is what associative property you all have to apply over here and then do it, okay. Now next I will be dealing with one more thing. So after that I will be doing this one. If A is associative, take this as note, okay. If A is associative algebra over F, then we define a new bilinear operation, okay. Lie bracket on A by Lie bracket of A comma B is equal to AB minus BA for all A comma B belongs to A. Then A together with Lie bracket is a Lie algebra. Now let me turn the page and do the next one, that is the derivations. Okay, let A be an algebra over a field F. A derivation of A is a F linear map D, A tending to A, such that D of AB is equal to A into D of B plus d of a into b for all a comma b belongs to a. A is nothing but a algebra, right? Now, let derivative of a be the set of all derivations of a. Derivative of a is a vector subspace of GL of a. Moreover, derivative of derivative of a is a Lie subalgebra of GL of a. Now let me start with the exercise 1.8. Let D be and E be derivations of an algebra A. I have to show that D comma E is equal to D composite E minus E composite D is also a derivation. Okay, so what I have to do is I have to take these two things and I have to multiply it. Like it's like I have to take now put it as it is over here, plug it here and multiply AB on both the side. Okay, this and this. Now this is equal to what? This is equal to what? Derivative of E this into this I have to do first. D composite E into AB and minus E composite D into this AB. Okay. Then use this thing. Apply this rule. Which one it is? This one. Okay. And I will get what? D composite E. Okay. D, I'll take it outside and it is what? E of AB. Now what is E of AB? I have, if I apply the derivation rule like D of that, so I will get D of E of A of B plus A of E of B minus D minus E D of A of B plus A D of B. Okay. Now this is equal to nothing but this. So same way I have to apply the same thing. I have to apply this for that. Now this is the derivation of AB is equal to A of DB in plus D of A of B. So that thing I have to apply. First what I have to do? I have to do for this one first. Okay, this plus this and then I have to do for this one. And similar way I have to do it for this one. Then what I am going to get is this. Now here what will happen? Just cancel the terms, whichever terms are being cancelling of whichever terms are getting cancelled. Okay. Now E of A into D of B. Now this term is getting cancelled with along with what? E of A. So again that term will be the minus E of A into D of B. This term will get cancelled. Then D of A, E of B along with this. Minus D of A into E of B. Okay. Once this is done, whatever terms are remaining that you all write it down. Okay. Like decomposite E, then write this as it is minus this you all write down. Okay, here. Then plus this minus this term. Then this is equal to what? Now this is same for both, right? Common this. So what I'll do is, okay, now what you all will be doing is decomposite E minus E composite D and then this you all write it in the bracket A into B, this plus A. Now for this one also you all have to do the same thing. This is common for both. So A into D composite E minus E composite D into B this. Now this is equal to what? I have to use what I need to use is general linear algebra. And what is general linear algebra? You all know what it is, right? It is Lie bracket of x comma y is equal to x composite y minus y composite x, right? It's not fitting over here, so it was something like this. X comma y is equal to x composite y. In the previous video I have already given you all this, okay? Minus y composite x. So this rule I have to apply, general linear algebra it is, right? From that. So same thing. So in this form, if it is there, then I have to write d comma e, leave bracket of d comma e into this a b, okay? In the bracket I'll put, okay? Plus a as it is, then what is this? Again I have to apply this. So it is also d comma e of b, right? Let me rub this part. Now next is I will be doing is structure constant. That is the last part of this chapter 4. Let L be, let L be a Lie algebra over a field f of dimension n with bases x1, x2 up to xn, and we define scalars aij of k belongs to a field f such that the Lie bracket of xi comma xj is equal to summation of k is equal to 1 to n aij of k. This is xk into xk. You all have to know this, okay? I'm just reading. Is it whether it is clear to you all? Next is the continuation of this part. You all have to note that the Lie bracket. Note that the Lie bracket this is completely determined by the product xi comma xj. Okay, now this is the product. Okay, now the aij of k are called a structure. Now this is called a structure constant of L. L is what? Lie algebra. With respect to this basis, we emphasize that the aij of k depends on the choice of basis of L. Okay, so now what I will be doing is, I'll turn the page. By L1 and L1 dash. Now what is my L1? That is from alternativity which I have taken. That is my xi comma xj is equal to 0 for all I. Xi comma xi is equal to 0 for all I, and this is your L1 dash, okay, which I have taken. Xi comma xj is equal to minus Lie bracket of xj comma xi. Lie bracket, okay, this. So that aii of k is equal to 0. For this one it is, okay, and for this one it is like this. aij of k is equal to minus aj of I of k. So it is sufficient to know that structure constant of aij of k for 1 less than or equal to I is less than j is less than or equal to n. With this I am done with today's lecture. That is lecture 4, and in next I will be starting with the lecture 5. I hope you all have understood today's lecture. And one more thing, I wanted to give you all one homework problem based on this. Let me give you all that. Okay, just take down this problem, okay? Second one. Show that from that derivative thing, okay? Show that decomposite E need not be a derivation. This is for your homework. You can try this. And thanks for watching.